this video, we are going to see solving Lagrange's linear partial differential equation by the method of grouping. So first of all, the Lagrange linear partial differential equation is of the form PP plus QQ is equal to R, where capital P, capital Q and capital R are functions of x, y and z. So whenever if we see PP plus QQ is equal to R, that is called as Lagrange's linear partial differential equation. So now we are going to solve a problem by the method of grouping. So first problem is y square z by x into p plus xzq is equal to y square. So now if you look at this equation, this is of the form capital P into small p plus capital Q into small q is equal to R. Okay, so here what is capital P? Capital P is nothing but y square z by x, and then capital Q is nothing but x into z, and then capital R is nothing but the right hand side function y square. So now P, Q, R are functions of x, y and z. Now we have to first consider the subsidiary equation. How to write the subsidiary equation is dx by capital P is equal to dy by capital Q is equal to dz by capital R. So this is called the subsidiary equation. Now we have to replace for P, Q and R. So what is P? P is y square z by x is equal to dy divided by Q is xz and R is y square. So now let us name these three ratios as 1, 2 and 3. So now by the method of grouping, how to solve this equation. So first we have to group any two ratios together such that it is easy to integrate it to find the solution. So now first of all let us consider the ratio 1 and 2. So if you consider the ratio 1 and 2, it involves the derivative dx and dy alone. There is no dz, so that we have to eliminate that z. So while equating ratio 1 and 2, we can easily eliminate that z. That is, we can easily cancel the z. So remaining will be function of x and y alone, which can be easily integrated with respect to x and y separately. So now let us consider the ratio 1 and 2. From ratio 1 and 2, it is dx divided by y square z by x, which is equal to dy divided by x into z. So this z and this z get cancel, which implies this denominator x can be taken to the numerator, so that here x dx divided by y square is equal to dy divided by x. Again we can separate the variables according to the derivative, so which implies again this x square dx, because this x can be taken to the left side as x square. So x square dx is equal to similarly y square dy. Now easily we can integrate it using variable separable method. So while integrating it, which gives you x cube by 3 is equal to y cube by 3 plus we can add some constant c. Okay, so this gives you x cube minus y cube divided by 3 is equal to c, means which gives you 3c, or otherwise we can name it as another constant a. So this is one solution. Now considering the first and the third ratio. The first ratio is dx divided by y square z divided by x is equal to third is dz divided by y square. So that here the derivatives are dx and dz, so we don't want the variable y here. So here it is easy to cancel that y square also, which gives you x dx divided by z is equal to dz. Right, so now we can cross multiply the z here, which gives you x dx is equal to z dz. So which on integration x square by 2 is equal to z square by 2 plus some c. Again, on simplification, x square minus z square is equal to 2c, which can be written as another constant b. So now mark it as equation 2. So now from equation 1 and 2 or the two independent solutions, the solution what we are going to find should be independent to each other. Here equation 1 and 2 are independent, and hence we can conclude that the general solution is phi of a comma b. What is a comma b here is a is nothing but x cube minus y cube. So x cube minus y cube comma b is x square minus z square, which is equal to 0. So now moving to the next question, y square p minus xyq is equal to zx. Here p is equal to y square, q is equal to minus xy, and r is equal to zx. So now we shall write the subsidiary equation, which we can write it as dx by capital P, that is y square, dy by capital Q minus xy is equal to dz divided by capital R, that is zx. Now we shall name it as ratio 1, 2 and then 3. So now comparing the two ratios, which ratio we can compare is, here we can compare 1 and 2 as usual. So while comparing ratio 1 and 2, dx by y square is equal to dy divided by minus xy. So here we can cancel one y term, so which can be written as, by cross multiplying this, x dx is equal to minus y dy. On integration, this gives you x square by 2 is equal to minus y square by 2 is equal to some c, which implies x square plus y square is equal to some a, because 2 into c is another constant. Mark it as equation 1. So this is one of the independent solutions. So similarly, we have to find out another solution. So for that, what we can do, we can equate what is that subsidiary equation, that ratio 2 and 3 we can equate. So that while equating ratio 2 and 3, what happened here is we can cancel x variable, which means that we can have the derivative y and z alone, so that we can equate the ratio 2 and 3. Now consider the ratio 2 and 3. 2 is dy divided by minus xy is equal to, third ratio is dz divided by zx. So here we don't want the variable x here, so that we can eliminate or cancel x here. So that here dy divided by y is equal to, this minus we can take it here or multiply throughout by minus 1. So this gives you minus dz by z. Now integrating this, what we get here is log y is equal to minus log z. Since we are having both logarithmic function, we can consider the constant again as log function. So let it be log b. Okay, so that here we can have log y plus log z is equal to log b. But log a plus log b, we know that we can write it as log ab. So here it is log yz is equal to log b. So now eliminating that log or taking exponential on both the sides, we obtain yz is equal to b. So this we can mark it as equation 2. Now 1 and 2 are both independent to each other, and so that we can conclude that the general solution to this Lagrange partial differential equation is phi of a comma b. A is nothing but x square plus y square, and b is nothing but yz, which is equal to 0. So that's it for this session. Thank you.